Okay, today we're going to talk about differentiability, which means having a derivative. Okay, so if a function has a derivative at a value of x, then we say the function is differentiable at that value. What do I mean by has a derivative? Well, I want you to remember that the derivative is a limit. Okay, let's write down the definition of f prime, because you're going to need to have this memorized. F prime of x equals what? It equals the limit of f of x plus h minus f of x over h as h goes to 0. That's what f prime of x means. Okay, so you see it's a limit. And what do you know about limits? You know that some limits exist and some don't. So that means that f prime of x will sometimes exist and sometimes not. Okay? And that's what the word differentiable and non-differentiable mean. So I'm going to write that down. So if f prime of c, meaning you're plugging a number c into f prime, if that exists, then we say f is differentiable at x equals c. Okay, and the alternative is if f prime of c doesn't exist, then we say f is, you can say it's not differentiable, or you can say it is non-differentiable. At x equals c. Okay? If the derivative exists at every point of the domain, then we just say that the function is differentiable. Do you hear the difference there? If I say it's differentiable at x equals 2, then that means there is a derivative right there when x equals 2. If I just say the function is differentiable, period, then that means the derivative exists at every value of x in the domain. Okay, and what I want to do is I want to go over with you today, when does this happen? When is a function not going to be differentiable? Okay, now in order to do that, I want to introduce you to an alternative way of writing the derivative. Okay, so this is what I wrote down as the definition of f prime. There's another way of writing it that's very common, sometimes more helpful, so I want to show you the other way of writing f prime as well. Okay, so what I'm going to do is I'm going to work it out here and show you how to get this alternative definition, and then I'll write the alternative definition up at the top. Okay, so I'm going to write f prime of x equals, and I'm going to leave that blank while I show you how to get what I want to get. Okay, so I'm going to write down our original definition here. Okay, and this is the limit as h goes to 0. Now I'm just going to do a little bit of algebra here. I'm going to replace h with x minus c. Okay? Why am I going to do that? Well, don't worry right now about why. Just trust me and you're going to see that it's a good idea. Okay? I'm going to replace the letter h with x minus c. Or if you don't like that explanation, I could word it this way, and maybe you'll like this better. I'm going to say, let C be the name that I give to h minus x. H exists. It's a variable there. X exists. It's another variable. And so h minus x exists. And if I choose to, I can give that any name that I want. And I'm choosing to call it C. Okay? So, if C equals h minus x, then that means... Oh, hang on one second. I'm sorry. I meant to say h plus x. Sorry about that. Okay, so got that fixed. Okay, so that means what? Let's just do some stuff over here. If c is h plus x, then doesn't that mean that h equals c minus x? So instead of writing h goes to 0, I can write c minus x goes to 0, correct? And if c minus x is going to 0, then isn't that the same thing as saying c is approaching x? So that's what I'm going to write down there. C is approaching x. Okay, so let me go over that really quickly one more time. I'm taking h and x and adding them together, and I'm calling that c. So that means that every h that I see can be replaced with c minus x. So h approaching 0 gets replaced with c minus x approaching 0. But if c minus x is approaching 0, then that means c is approaching x. And that's how I came up with this right here. Okay? Now, I see another h on the bottom of the fraction. And I said every h can be replaced with c minus x, so I'm going to replace that h with c minus x. Okay, let's look at the top. I have f twice with two different things inside. In the first f, what do I have inside? X plus h. Well, look, x plus h is c. Okay, and in the second instance, the f just has x in it. This is another way of writing f prime of x. Okay? So now you have two different ways of writing f prime. Okay? So you have the original definition, and now you have an alternative definition. In case it should happen to be more useful to you, you can use this definition for f prime. I'll tell you my opinion on which definition is better for different kinds of problems. I personally think that the original definition, now this is just opinion, okay, it's my opinion, I think that is more useful for finding the function f prime. Remember how I showed you in the other lecture? I said, if you want to find the derivative at one point, then okay, you find the derivative at that point, right? And I actually put a number in there instead of x. But then I said, if you want to find the derivative at several points, then rather than finding the derivative several times, it's easier to just find the derivative once with the variable x in it. And then that gives you a function called f prime, and then you can plug in different numbers into that function in order to find the derivative at different values. And when I'm doing that, I prefer the green definition. Okay? Now I think that this blue definition down here tends to be more useful for finding, and by the way, I see that I left the ing off of finding up here. Let me fix that grammar. There we go. So I think the blue definition is more useful for finding the derivative at one location. And I'll show you why I think so. Because you can always take that blue definition there. Let's get rid of this stuff here. I can always take that and write it this way. Let's write down this much here. Okay, so let me just do a couple of things, and at first you might not understand why, but you'll see why it's useful. Do you agree that in this part over here, I have a fraction, and on the top and bottom are both minus problems? I can switch the order of the top. Whoops, wrong color. If I also switch the order of the bottom, right? You agree with that? So that I didn't really change anything, did I? Here's the other thing. Look at the part underneath the word limit. Up in the blue area, I wrote c is approaching x. Now, if c is approaching x, isn't that the same thing as saying x is approaching c? So I can do that. That's the same thing as up above. Okay? But here's the difference. In blue, whoops, in the blue area where I wrote c is approaching x, then c and x are getting closer together, but from the frame of reference where I'm saying that c is moving closer to x. I don't know if you've ever taken a physics class, but they talk about different frames of reference. You see, like think about this. Suppose that an asteroid is about to collide with Earth. From the point of view of the Earth, it looks like the asteroid is coming towards the Earth and is going to hit it. But if you were standing on the asteroid, it would look like the Earth is coming towards the asteroid and going to hit it. It's the same situation. But depending upon your frame of reference, you can interpret it in different ways. So up there in the blue area, I wrote x and c are getting closer together. From the frame of reference where I would be standing on x, and it looks like c is coming closer to me. Okay, down here, same thing's happening, it's just a different frame of reference. Down there, it's where I would be standing on C, and it looks like X is getting closer to me. Okay? In that frame of reference, let me highlight this in yellow, because it looks like X is the one doing the moving, and C is the one standing still. Then in that case, it would be proper to write f prime of C. And that's what I mean when I say that I find that to be more useful if you're trying to find the derivative at one single location. Okay? Now, let me look at where we are on time. Okay, it's only been 15 minutes. That's fine. So let's practice that so you can get an idea for using. So there's really 3 different ways, right, of writing the derivative. So let's practice using different ones. Okay, suppose we have f of x equals x squared. And I'm going to answer 2 different questions. What if somebody said to me, find f prime of x? What if somebody else said, find f prime of 5? I'll show you how I personally would handle both of those questions. Okay? If somebody asks me to find f prime of x, then that means they're asking me for a function. And so I personally would do that problem using the green definition. Okay? I would write this. F prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h, which equals the limit as h goes to 0 of x plus h squared minus x squared over h. And simplify. On top we have x squared plus 2xh plus h squared minus x squared, and that's over h. The x squareds cancel out on top because one's positive and one's negative, so I really just have 2xh plus h squared over h. I can factor out an h on top. And that h that I just factored out will cancel out with the h on the bottom. And it leaves us with just this. Now I can find the limit. As h goes to 0, what will we end up with? 2x. So there's f prime of x. Let's write that in blue. F prime of x equals 2x. Okay? It takes some work, but it's just mostly algebra. There's no calculus until the very last line. Now, if somebody asks me this other question, find f prime of 5, I could do the problem the same exact way, except have a 5 there instead of an x. Or I could do it the same way with x, and then plug in a 5 at the end. But how I would choose to do it personally is I would use that definition in yellow, and I would write f prime of 5 equals the limit of f of x minus f of 5 over x minus 5 as x goes to 5. That would be the limit of x squared minus 5 squared over x minus 5, which is equal to the limit of x plus 5 times x minus 5 over x minus 5. And then you see the x minus 5's cancel. So I really just have the limit of x plus 5. As x approaches 5, what would that limit be? It'd be 10, wouldn't it? You see how I can do that a little bit faster that way. So let's write that. F prime of 5 equal 10, which is of course what I would have gotten if I would have just plugged 5 into here. It's just two different ways, okay? And that's my opinion on which method I prefer to use and what kind of different setting, okay? For the rest of the discussion today, what's going to be important is just for you to realize that there's 3 different ways that you can write down a derivative. Okay, either like it is in green, like it is in blue, or if you're only going to be plugging in one number, then you can do it the way it is written in yellow. Okay? All right, I want to change gears a little bit now. I want to talk to you about what would make the derivative of f not exist. And the first thing I want to show you is this. It's extremely important. In fact, it's a theorem. I'm going to write it down here. I'm going to get rid of this stuff here so it's out of our way. If you need to see it again, you can always rewind and look at it. But we need this space here. So I'm going to show you a theorem, which is this. If f prime exists at any location, then f must be continuous at that location. Okay? Just give me a second to finish getting rid of this stuff and I'll write that down. Okay. So this is a very important theorem. If f is differentiable at x equals c, then f is continuous at x equals c. You need to know that fact, okay? I'm going to show you why it's true. We're going to use a theorem about limits that I'm going to remind you of here. Okay, there was a theorem or a rule, I think we called it, that said if you have two functions and let's say the limit, we'll call them f and g for right now. If we say the limit of f of x as x approaches, let's say c, if that limit exists and equals, let's say, L, and if the limit of a second function as x approaches c exists and equals, let's say, m, then the limit of their product will automatically exist, and it will equal the limit of f times the limit of g. which in this case would be L times M. Okay, that was a rule of limits. Okay, and we're going to use that rule to prove our theorem. Okay, and I'm going to use the yellow form. I'm going to use this form right there. Okay, and this is actually going to be really easy to prove this theorem. Okay, proof. Suppose that f prime of C exists. Then f of x minus f of c equals f of x minus f of c over x minus c times x minus c, right? And if f prime of c exists, then that means the limit of that exists as x approaches c. Because look, that's what f prime of c is. It's the limit of this as x approaches c. Okay, and of course the limit of this exists as x approaches c, because that limit would be 0, wouldn't it? So we can say, so the limit of f of x minus f of c, the limit as x approaches c, would equal the limit of f of x minus f of c over x minus c times the limit of x minus c, which would be f prime of c times 0, which would equal 0. Any number times 0 is 0. So the limit of f of x minus f of c as x approaches c equals 0, and that means the limit of f of x must be f of c. And isn't that the very definition of saying f is continuous at c? It is. That's what it means to be continuous at c. It means the limit of f of x as x approaches c equals f of c. And that's the end of the proof. Mathematicians like to put a box like that at the end of the proof. It's like a period for the proof, saying that that's the end. Sometimes people like to fill it in. Okay? So that's an important theorem. Please remember that. In order to have a derivative at a certain location, the function must be continuous at that location. Now, if you just flip that coin over, what does that tell you? The other side of that coin is, if a function is not continuous at a location, then it can't be differentiable. And that's the first thing that I really wanted to get to here, okay, is when would f fail to be differentiable? There's several ways that it could happen, but most commonly there's two things to worry about, okay? Which is this. If f is not continuous at C, then f is not differentiable at C. Okay, and you can imagine why if you just think about it. Here's a simple way of drawing a function that's not continuous here. I'll just put that function like that. What kind of discontinuity is that, by the way? That's a jump discontinuity. Okay, now here's the thing. F prime of C is supposed to tell us the slope of the tangent line at C, right? Well, how could you possibly draw a tangent line in that kind of a situation? You can't. There's no such thing as a tangent line in a situation like that. If the function is discontinuous, then there's no tangent line, and if there's no tangent line, then there's no slope of the tangent line, in which case there's no derivative. Okay? The other time that's very common is if the graph of f has a cusp at the point x, I meant to say C, comma f of C, then f is not differentiable at C. And I'll tell you what a cusp is in just a second. A cusp is a sharp point. So let me draw a picture for you here. Okay, suppose f looks like this, maybe. And there's the point right there, C, f of C. That's a cusp. Sometimes they look something like this. Okay, that's another example of a cusp. All right, let's actually draw it like that with more of a curve to it, just to make it more interesting. I'm not going to change anything fundamentally, but I'm just going to draw like that. Okay, all right, so there would be no derivative at that point, and here's the reason why. I'll show again. Just remember, the derivative is supposed to be the slope of the tangent line, right? Well, here's the thing. If you tried to find that slope coming from the left, the tangent line would look like this. But coming from the right, the tangent line looks like that. There is no one single tangent line at that point. Okay? And if you can't say this is the tangent line, then you can't tell me what the slope of the tangent line would be. And if you can't find the slope of a tangent line, that means you can't find a derivative. Okay? Those are the two most common situations where a function fails to be differentiable. Now there is a third. I'll go ahead and point it out. It's not nearly as common, but it's simple though. And that is if the graph of f is vertical. at the point C, f of C, then f is not differentiable. At C. And again, that's really easy to see why if you just put it onto paper. Suppose f goes like this. And right there at that point, it's vertical. Then the tangent line would be straight up and down. What's the slope of a vertical line? There isn't one, right? There is no such thing as the slope of a vertical line. It's undefined. What does undefined mean? Undefined means non-existent. The derivative is the slope of the tangent line. So if the tangent line doesn't have a slope, then that means there isn't a derivative. So those are the three most common, and the first two are the most common of those, but let's not forget about the third one. Those are the three common ways that a function could fail to have a derivative at a particular point. So that's important. When you look at graphs and you see things like cusps or discontinuities or vertical portions of the graph, you should know, well, there's not going to be any derivative at those places. Okay? What else did we learn? You also need to definitely know this theorem. If f is differentiable, then it's continuous. And thirdly, I showed you a couple of alternative ways of writing derivative, if you prefer. All right. That's the end of today's lecture.